Good afternoon. We are continuing with our college algebra lectures. This is lecture 3. We're still in the review or prerequisite section, which comes before the heart of the college algebra course or most courses. So this should be review if you took an intermediate algebra class or high school algebra. A lot of the stuff will be review. Lecture 3 will just be about exponents. So we'll go over product, quotient, power, zero exponents, negative exponents, power products and quotients, and simplifying expressions that have exponents in them. So this lecture will have a lot of examples. And we'll start here with the product. We'll call it the product rule, just to be consistent with the text. The product rule says if I have two of the same bases raised to some power, that I can add the exponents. So here, A is a base, and M and N are the exponents. Or simply powers. The power of A is M, the power of A is N. So when the base is the same, we could add them, but they must be the same. You can't add exponents of different bases. Here's an example. We have 2 to the 4th times 2 to the 6th. This is 2 of 4 plus 6 and 2 to the 10th. Equivalently, we can have variables. So x squared times x to the 4th times x to the 6th will be 2 plus 4 plus 6, which would be x to the 12th. So same bases, we can add the powers when the bases are being multiplied. That's why we call it the product rule. Let's go on to the quotient rule. So the quotient rule is the case when we have two bases, the same bases, that are being divided, or we have a quotient. In this case, we subtract the exponents. So a to the m divided by a to the n is equal to a to the m minus n. Some examples: x to the 5th divided by x squared is equal to x5 minus 2 is equal to x to the 3rd. It's a way of simplifying, but also we can have something a little more complex. And we'll see later in this lecture that there are other ways to simplify something like this. But for now, we're just interested in the quotient rule application. So this will be x times the square root of 2. 5 minus 1 is equal to x square root of 2 to the 4. Now, a question you might have is, where did I get that 1? Well, if there is no exponent, we assume 1. So in this case, this is really to the 1, because anything to the 1 is itself. 2 to the 1 is 2. The square root of 2 to the 1 is the square root of 2. So we assume without notation that there is an existing a 1. And we'll see a little bit later how to further reduce something like this. But for now, we're just looking at the quotient rule. Let's look at what we're going to call the power rule. So if I have a to the m, and then the quantity to the n, this will be the same as multiplying m and n. So you should see this is not the product rule. This is not a to the m times a to the n, which we add m and n. This is a to the m to the nth. So let's look at an example So x to the fourth squared. Now the rule just simply says that if this is the case, that I multiply these and I get x to the eighth. But why? Why is this the case? Well, let's remember what a power does. A power says that I'm going to take something. If I raise it to the power of 2, I'm going to multiply whatever it is by itself that many times. So in actuality, what we're doing is multiplying x to the fourth to itself twice. And this multiplication means we're doing the product rule. So we're adding the exponents. And so this is 8 to the x. You can see the top part of the example is quicker. We multiply 2 and 4. The bottom part is legitimate. It just has that little extra step in there. But it's the same. It's equivalently the exact same. So the power rule is nice. Let's do something a little more complex looking. And again, we can look at other ways to handle this simplification later. But the rule says I take whatever in the inside, the power, and I multiply it to whatever the outside power is. So this is 8 times 2. So that's 3y to the 16th. And again, we'll look in a little bit how to further reduce this or simplify or expand, however you want to look at it. So that's the power rule, the quotient rule, and the product rule. We're moving along. So let's look at what happens when we get 0 exponents. The rule is for any real number a, if I raise a to 0, it's equal to 1 for any real number a. And this is handy when we have a situation like this. We'll apply the quotient rule, which we just learned. It's 4 minus 4, and that's x to the 0, which is 1. Now, it should be obvious from the left that something divided by itself is always 1. In other words, 2 divided by 2 is 1. X to the fourth divided by x to the fourth is 1. But here's a more interesting reason why that's true in this case, because we'll have an exponent to 0. Let's look at something that's going to result in a 0 exponent, but is a little bit more complex looking. So x squared, x to the third, and x squared y to the third times x squared y to the third squared. So let's leave the numerator alone. And let's look at this. Remember, we assume there's a 1 there. And so I have a product of something in the parentheses. They're the same, so the base is the same. So that means that we take x squared and y to the third, and we add the exponents. And then we have y, x and y to the third. Now we apply the quotient rule that says that if I have a division of the same base, I can write that as a subtraction of the powers. So they have 3 minus 3, which is x to the third, x squared, y to the third of 0, so that's 1. So that means that x squared y to the third divided by x squared y third times x squared y third to the 2 is just 1 in every case. No matter what values of x and y you plug in there, it would always equal 1. So now we're going to look at some negative exponents. The general rule here, I'm using a base of a again, a to the negative n we can think of as being 1 over a to the n. Effectively, we take the negative exponent and we put the base and the exponent positive in the denominator of a fraction. So an example, and you can see we're sort of stacking rules now. So the first thing we need is the quotient rule. So we have 4 minus 7 is x to the negative third. And then the above rule says, well, I can write that as 1 over x to the third. These are equivalent expressions. If you go on and take calculus or look at calculus or study calculus, sometimes it's advantageous to have x to the negative third power. Sometimes it's better to have x to the third in the denominator. So why does this happen? Let's look at the same example, but let's take this more literally. We have x to the fourth, which means that we're multiplying the base 4 times. Same with the denominator, we're multiplying the base 7 times. And this is a situation. Now, just straight cancellation law says I can, for every 1 on top, I can get rid of 1 on the bottom. So let's get rid of this guy, 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 this guy. And we're left with 1 over x times x, which is really x to the third. So that's why when we do the quotient rule and subtract and we get a negative exponents, it's the same as if we have spell those out as a product, cancel, and we get x to the 1 over x to the third. So that's the why. A lot of these are just shorthand. The quicker way to handle exponents. That's sort of why we're reviewing this. Is it's easier when we're looking at polynomials or we're trying to graph things and we have a bunch of powers and we want to simplify or expand. These are quick ways to handle those things. Let's look at another example. Again, this lecture is going to be heavy on examples. And let's say we have negative 5x to the 2 of 9. So it's negative 5x squared to the 4 minus 9. So negative 5x squared to the negative 5 is 1 over negative 5x squared to the 5th. Not too bad. Just applying the rules. You can always pause, go back, and look at these examples again. Really helpful. The rule is nice. You can state a rule, state a definition, theorem, corollary, lemma. It's always nice to see the application. I think it sinks in a little bit better. So this is product rule. Product rule says we add the exponents when they have the same base. So we're going to add this, which y to the 2 plus negative 8 is the same as 2 minus 8, which is the same as negative 6, which is the same as 1 over 6. So that's the negative exponent rule. Pretty straightforward again. Exponent reviews are helpful. These are maybe stuff you would want to review even as you head on to more advanced mathematics. If you take a Calc 1 or Calc 2 course in college, it's nice to review these. All right, the power of products, which means if I have 2 bases, a times b, and I'm taking that to some power n, the power product rule says I can take each individual to the same power. So a to the n times b to the n. An example, xy squared is the same as x squared, y squared. So why is this true? Again, let's recall what we're doing when we're squaring stuff. We're multiplying it by itself however many times the power indicates. So in this case, we're multiplying x and y and x and y. Now, in lecture 1, we talked about some of the properties of real numbers. We know that it's associative and distributive. So I can get rid of these brackets and write this way. That's the associative. Now, the commutative says that I can arrange these this way. So the commutative property allows us to do that. And x times x is just x squared, and y times y is just y squared. So again, this is a shorthand. X, y squared, products, this gives us x squared, y squared. The y is the longer process on bottom, knowing that we're doing the associative rule and we're doing the commutative rule to get up to the same result. Let me write that just so we know. We use associative and commutative properties. And refer to lecture 1 in this series. If this is not familiar to you, we go over that in that lecture. So let's look at another example. Again, we'll try to mix some things in here so it looks a little bit more hairy. So when we're spelling out the rules, it makes a little bit more sense. So I have a product 2 times x squared times y to the third. Now the rule says I can take to the 4th power each of these terms individually. And I'm going to be careful how I write this. Don't be afraid to use brackets. You're not going to get penalized for bracketing things, especially when you're starting out. Now I'm just going to leave that as 2 to the 4th. Now the rule says I take x squared to the 4th is our previous rule that says now I multiply those two things. Same with y to the 3rd to the 4th. I multiply those. So we get 2 to the 4th times x to the 8th times y to the 12th. And 2 to the 4th we can evaluate. 2 to the 4th is 2 times 2 times 2 times 2, which is 16. So these are equivalent expressions. It might be a little clearer, 16x to the 8th, y to the 12th, than what we had before. And that's sort of the goal of this section, is just to take exponents and handle them so they look a little bit more manageable. That's relative, of course. Sometimes it might look worse, but that's math sometimes. Another example, we're going to mix in some other ideas that we just explored. So I'm going to apply the rule literally, meaning that I have this quantity of products taken to the -2. So I'm going to take each to the -2, being very careful of how I write each term. And once you're good at this stuff, when it's a little bit clear to you, you don't have to do intermediate steps like this. Now, the rule says I take 2 times -2. I'm erasing. Times x. Now I multiply -2 and -2 times y, and I'm multiplying 3 and -2. So we got 2 to the -4 times x to the 4 times y to the -6. Now, the negative exponents we can write. So this is x to the 4th stays on top, and we know that 2 comes down and 4 stays positive. Y to the 6th. So this is x to the 4th, 16, y to the 6th, which is much better looking than this. Simplification in this case is very, very warranted. Let's do an example with some more variables. again, another look. So let's say we have f g to the third to the fifth, and then we have f times g 2 to the negative 2. So I'm going to do the numerator and denominator first using this rule. So being careful, I'm going to write it with brackets, each individual term to the fifth. Do the same to the denominator. And again, once you get a little bit quicker at this stuff, there might be a lot of these steps in between can go away and make your life a little bit easier. So now I'm multiplying them. So 2 times 5, that's the rule. 3 times 5, f negative 2, and then g negative 4. Now the rule says I have the same bases. They're in a quotient, so then I can add the numerator exponent and the denominator exponent, or subtract, my fault. Minus minus 2 times g to 15 minus minus 4. So 10 minus minus 2 is the same as 10 plus 2. G to the 15 minus minus 4 is 15 plus 4. So this is f to the 12th times g to the 19th. Again, this is much, much prettier than that. All right, next we have what's called the power of quotients. This says that if I have a fraction that's raised to some power, let's say m, maybe a little bit clearer here. So I have a fraction raised to the power of m that I can take the power to each individual base. So let's look at an example, and then we'll look at why that's true. So I have xy squared will be the same as x squared and y squared by this rule. So why? Why is that true? Again, this is going to be a shorthand, right? We're taking x over y and squaring it. So we're multiplying it by itself twice. Then we're using associative laws. We're writing it this way, which is x squared, y squared. So you can always apply the rule literally and then work from there, and you'll see that you'll get to the same spot. The quotient rule here is the power of quotients are a little bit quicker. Let's look at another example. Let me clear this a little. So we have x and x to the third to the fifth. So we'll do this literally just to apply the rule that we just learned. So that means I take x to the fifth and then x to the third to the fifth. Again, we're just stacking laws here. So this is 3 times 5 by the rule. And let's go a little further, because we know that if I have the same base, that I can subtract. And then we get negative 10. And the other rule, the negative exponent rule, says that we can take this as a power in the denominator. So this is x to the 10th. So what we're saying is that these are exactly the same. There might be some situations where you prefer x over x to the third to the fifth. There's also different ways to which to simplify this in the order in which we simplify. I'm just applying that rule directly. All right, so let's put all of this together and look at simplifying exponential expressions. The concept of expressions, I think we went over in lecture 2, the difference between an algebraic expression and, say, an algebraic equation. So we're going to use the laws, or use the things we just learned. So we have something like 9x to the negative 5th, z to the 3rd. We're going to multiply that by 3x to the 4th, and z to the negative 4. All right, the first thing I want to do is I want to group this a little bit better. We have the distributive property from lecture 1 or 2. So I'm going to group 9 times 3. And so this is distributive, associative, commutative, all of these real number properties. So I get x to the negative 5th and x to the 6th. We got z to the 3rd times z to the negative 4th. You do erase. All right, so 9 times 3 is just a constant, 27. And the rule then says that if I have two bases that are being multiplied, I can add them. And then we're going to add 3 plus negative 4. So we get 27x. I'm not going to write the 1. Negative 5 plus 6 is 1. But we'll just leave it that way. 3 plus negative 4 is negative 1. We're going to, again, use the rule that negative exponents we can put in the denominator. So this is 27x divided by z. Another perfectly reasonable way to write this would be 27 times x over z, whatever your preference might be. But just using the rules, using our properties of real numbers, we get the simplification 27x over z, which again, much better than that expression. Another example, mix up some variables and keep using x, y's, a's, and b's. What's h and j? So 7, h negative 1, j squared squared. I'm going to apply the rule on the numerator and denominator, literally moving 4 to each, being careful with my notation. Do it here as well. I tend to write a lot when I'm doing examples, but even when I'm doing my own mathematics, I tend to write a lot just so I have a clear path of where things are going. 2 to the 4th again is 16. h2 to the 4 means that I multiply 2 and 4, so it becomes h to the 8th. 2 times 4 is 8. J to the 1 times 4 is the same as 4 times 1 is 4. And we have 49. Negative 1 times 2 is negative 2, and 2 times 2 is 4. I'm going to put the numbers, the constants out here. And then let's look at, we have h base, h base. It says the rule that I take 8 and I subtract it from the power of the denominator base. Same with j. 4 minus 4, so we get 16/49. 8 minus minus 2 is 10 times j to the 0. And recall that anything raised to 0 is 1. So this is 16/49 times h to the 10th. Again, much prettier than the original expression. Much easier to handle, much easier. If I want to replace h and j with some numbers, some real numbers, I can do so in the original, but you can see in the simplified version, replacing h is much simpler in this case. Still raising something to the 10th power can be tricky. Nevertheless, it always looks easier. And you can notice j drops out. So j will always cancel regardless of what real number we pick for j, it will always cancel. All right, let's look at one last example. let's say b squared c to the negative third divided by b to the negative third. We'll say quantity. Let me be careful how I write these brackets, because we want to be able to make sure that it's clear that what I'm doing is I'm taking this quantity to the 2. I'll put this down just for convenience. Now, the rule says, again, I take a b squared c to the negative third squared divided by negative b, no, not negative b, b to the negative 3 squared. And then I multiply 3 and 2. So we'll take this little by little. So that's negative 6. And then I multiply this guy, that's b negative 6. Now I have a product and a power. So I'm going to take each individual term to that power, being careful again to keep my terms straight, and then b to the negative 6. So we have a negative 6. B is 2 times 6, so b becomes negative 12 times c to the negative 6 divided by b to the negative 6. Now I have the same base b, so let's do that. We know that we subtract the denominator base power from the numerator, and then we have this. So again, a to the negative 6 times b, we're going to have b to the negative 12 minus 6 will be negative 12 plus 6, which is negative 6, and c to the negative 6. These are all negative exponents, so let's move them all to the base, or the bottom, sorry, 6, b6, c6, which we can be done, or we can be cute and be like, well, that's really just ABC to the 6th. And since 1 to the 6th is just 1, I can actually write this as 1 over ABC to the 6th. Any of these are a conclusion point. Again, it depends on your professor, depends on what the question was asked, depends on what you want to do, but that's it. A much simpler expression than what we started out with. As you can see, the very ugly quotient becomes something much more manageable, especially if we are replacing a, b, and c in this expression to evaluate it. So that's the end of this lecture. Next time, lecture 4, we will be doing radicals and rational exponents, which will require us to remember the laws that we learned in lecture 3. So next time, radicals and radical exponents. So thanks for watching, like and subscribe, and I hope this helps.